Problem 6.3-2. A vertical shear force acts on the cross-section of the beam. Determine the maximum shear stress on the cross-section. We have a circular shaped cross-section. It's hollow. And shear force is 28 kilonewtons. We're given the inner and outer diameter. To get an answer for this problem, we will be using the shear formula, which has internal shear force, Q, moment of inertia, and member width in it. We need to find these terms. V is given, that's 20 kilonewtons. Next, I'm going to find the moment of inertia for this cross-section. The moment of inertia can be calculated using the parallel axis theorem as the moment of inertia of the outer circle minus the moment of inertia of the inner circle. That's moment of inertia for a circle is pi divided by 4 times the radius to the fourth. And that gives us this value for moment of inertia for the cross-section. The maximum shear stress in this cross-section will be at the neutral axis because we have a pipe cross-section. Then the neutral axis will be right at the center. So for Q for our cross-section, we're going to find Q for the top half of the pipe. We will calculate Q, which is equal to the area above or below the neutral axis times the centroid of that area. Now, because we have this half pipe shape, the area, that's not too hard to find, but the y bar prime, or the centroid of that half pipe shape, is a little more challenging. To simplify this problem, I'm just going to find Q is equal to Q of the outer semicircle minus Q of the inner semicircle. Reference materials on geometric shapes will give us the location of the centroid of a semicircle, and it's equal to 4r divided by 3 pi up from the bottom of the semicircle as shown. So Q for the outer semicircle is equal to 1/2 times the area of that circle, which is pi times the radius squared. That's our A prime. Y bar prime is the location of the centroid. 4 divided by 3 and divided by pi times 0.1 meters, the radius. Notice that the pi's cancel out. And here's our value for the outer Q. And we also get our inner Q the same way. And we get our value for Q as the difference between Q outer and Q inner. Now we can solve for maximum shear stress. Filling in the variables for the shear formula, V is 20,000 newtons, Q we found above, I we found above, and T is the width of the member at the point we're evaluating stress. And if we look at our cross-section, we're evaluating stress at the neutral axis, so the width of the member is the two wall thicknesses. I can get that by subtracting the outer diameter minus the inner diameter. And we get a value of 6.69 megapascals. That is our maximum stress, and we're done.